Okay. Good morning. Hi, welcome. Can everybody hear me okay? All right, cool. Thanks everyone so much for joining. This is Advances and Challenges of Cloud Native Geospatial Data, which is the first of two sessions for the Cloud Computing Cluster. The title is actually much longer, but as Doug will tell you, I am not one for brevity. So this is the brief version of the title. We also have analysis ready cloud optimized data in there. People love that acronym ARCO that was popularized recently. So if you want to debate analysis ready versus cloud optimized, what each means, you can do that in the discussion group later on. So yeah. Just get Zoom window out of the way. Yeah, so there is a QR code that you can use to scan quickly and sign into the notes document. We'd love to know who's here. So if you could sign into the notes, I'd really appreciate that. These slides are also available via that tiny URL if you want to click on any of the links that are later on. Cool, so we're gonna go through a little introduction before we jump into the talk. So why this session, what to expect from this session. I'm going to talk about what part 2 is going to look like, the discussion groups from 11 to 12:30, and then how to stay involved with the cloud computing cluster. So first of all, why did you choose to come to this session? So just take a minute. I'm just going to give everybody like 10 seconds. Think about why you chose to come. So I'm going to give my answer, knowledge sharing. So I think a lot of times with the cloud computing, with the clusters in general, we want to come out with an outcome, which is great. But I also think that knowledge sharing for the sake of knowledge sharing is really important when we're in an evolving space. We don't have any, right now, we don't have any single solution to all cloud native geospatial. A lot depends on the problem context, and the problem solver. So here's the list of the talks. I'm going to, I know that we're all really excited to basically hear from all these folks, so I'm going to try and keep it brief. And also, if you have a topic that you're interested in discussing further, there's the tiny URL for the topics that we're going to have a discussion group in our second session from 11 to 12:30. We're going to break out into smaller discussion groups. So if there is a particular topic that you want to discuss more, please add your topics there. These are also not necessarily meant to just be discussions. They could also be working on a document or testing out Kerchunk or writing a Pangeo forage recipe. Like if you want to make it a working session too, to try something you haven't gotten to try before, definitely excited to see some people actually use this as a working session or just have it as a nice time for some group discussion about some of these cloud native geospatial challenges. So my request of participants is discover something to read about or try, make connection with the speaker or other participant, come up with a topic for the second session, and then of course join the discussion groups. So the discussion groups, you can add or vote on topics that are proposed in the topics spreadsheet that's there. I have a couple myself that are listed in there that I would love help with. And then join us at 11 a.m. where we're going to brainstorm on more topics. People are going to pitch their topics. Then we're going to configure groups, and then we're going to have 55 minutes to basically work together as a group on your discussion topic or working session idea. And then we're going to reconvene at 12:15 for report outs. So how to stay involved, we have a YouTube channel, so if you want to go back and see what we've done in the past as far as knowledge sharing sessions, that's a really great resource just to see what we've talked about in the past. We meet once a month on Mondays at 1 p.m. Eastern via Zoom, and those are usually knowledge sharing sessions. So I want to give a big shout out to people who helped me organize the session, Charlie, Jim, Rich, Dave, as well as Alexi. They came up with a lot of really great ideas and helped coordinate the session, so thank you. And all right, we're ready. So I'm going to pass it off to our first speaker, which is Matt.
Did we download it? Oh, I was looking for your last name. Sorry. I think I'd figured that out.
All right, good morning, everybody. I hate mornings. Personally, I'm a night person. My best time is between the hours of like 10 p.m. and 2 a.m. So this, I'd normally still be sleeping. Anyway, so this is a really sort of high-level intro to what you're going to hear about. There's all the speakers are going to be talking a lot more in depth, but I really wanted to talk about sort of a big picture, like why is this stuff really useful? Like you hear the term cloud native geospatial or cloud optimized data, and why is it that we do this? So let me define this concept of a queryable Earth. This is a term that Planet used some years ago, and I put down some questions here. Now these are big questions that we can answer with geospatial data, and ultimately sometimes we lose sight of the forest through the trees. Because ultimately, these are the kinds of questions that we're after, right? Like we worry about pre-processing data, and we worry about creating level 2 products or derived products. But really, what we want to do is we want to answer these questions. Now, notice what's missing from these questions. What's missing is a source of data. Like this doesn't say, oh, use Modis and do this thing. No, we just want the ultimate answer. So this really kind of is the goal, right? Like this is what we want to do with geospatial data. So what is cloud native geospatial? You've probably heard the term. And I like to describe it to people. I just say it's Google Earth Engine, right? Because this is the earliest example of a cloud native geospatial system. We have complete workflows that are performed in the cloud. You do the data discovery, processing, analytics, visualization. You have direct access to the data. This is an important key point here. They're in cloud optimized formats. Users can directly access this data, and this promotes scalability. We see this in Google Earth Engine, right? It's reproducibility because you can track provenance, ideally. And I really like this term. Some of you may have heard me say this before, and I didn't invent it, this term of executable papers. So in science, right, people publish papers, but really the great model to move towards is this idea of executable papers where the data is available online, the code is available online, and somebody can just hit a button and they can run this in their environment and they can rerun all of your analysis. So cloud native geospatial really means this easy discovery, access, and exploitation of data, of course, in the cloud. But the problem with Google Earth Engine is that it's not open source. It's not based on any sort of standards. You can't deploy it into your own environment. You can't build services on top of it, or at least not very easily, not without working with Google. So the community really has come together the last several years in developing these standards and the tooling to essentially create an open source version of Google Earth Engine. And there's a few different components to this. There's a metadata standard, to talk briefly about Stack. There's cloud optimized data formats, which is the focus of today that a lot of folks will talk about. And I'm not going to talk about this whole concept of ARD because that's really a can of worms. But that's an important piece, is to really have well characterized data. And it's related to the metadata, but I'm happy we can talk about that offline. So you've probably all heard about Stack. AWS has this great open data program, right? All this data is available online. But is this, okay, it's working, all right. So it's an animated GIF. So the problem with the AWS open data program, sorry, Chris, and actually a lot of data that's published online is that it's literally just like a bunch of data dumped online. And in the case of Sentinel and Landsat, the way that you find the data that you want is by file name, because it's in some sort of directory that we can pre-generate. We know what it is because they're tiled. It's a tiled system. This is really not a great way to discover data. You know where your data is. You find the tile. You go and get the tile. Yeah, well, what happens when this happens, right? Like data is collected in swaths. The tile is only half filled. My AOI is on the right-hand side. I download this data, it's empty. If my data is not tiled, the situation is, of course, worse. Like, how do I even know where the data is that I want? And so the key takeaway here is that if your metadata isn't indexed, then your data might as well not exist. Okay, so this is a key point. Your data needs to be indexed and geospatially indexed. So this is where Stack comes in. I'm not going to dive into this. I think most people are sort of familiar with at least the basics, but it's this language for describing geospatial data, and it's also a API for searching that data. Stack came out with a 1.0 version last year. The Stack API spec is still on a release candidate because it's tied to the OGC Features API. But we've had really great success with Stack, and it's primarily because of the implementations in the software ecosystem and adoption. Cloud optimized formats. Again, this is gonna, people are gonna do dives into various aspects of this, but I just wanted to give a brief intro on like what makes something cloud optimized. People will say cloud optimized data format. Okay, well, what does that mean? So traditionally, data is stored in these striped bits, right? And we have an AOI, and we have to read both of these striped bits in this example, these striped sections, because each of those stripes, each of those chunks are compressed individually. And so we need to read the entire thing and decompress it. And so all cloud optimized means really is that we optimize the shape and the size of these tiles in order to minimize extra data that we need to read. This is really all it means. It's a really simple concept. A cloud native data set is all it is one with small addressable chunks. Now these chunks can be internal chunks to the files as we see in HDF or cloud optimized GeoTIFF, or they could be external chunks on disk such as with ZAR. The cool thing about cloud optimized formats is like TIFF isn't a new format. Like ZAR is a new format, but if you look through GeoParquet, it's based on Parquet. These are not new formats. At a cloud outreach day a little while ago, somebody made a joke about cloud optimized tar. Well, guess what? It is actually a real thing. Somebody made a joke about it, but then we looked it up and somebody has created a cloud optimized tar. So the great thing about cloud optimized file formats is you can actually take legacy formats and all you need to do is index where these chunks are internally in the file and you have a cloud optimized format. And so this is, if you've heard of Kerchunk, this is a way to essentially turn NetCDF and HDF files into cloud optimized files. Lastly, I just want to briefly talk about cloud native geospatial workflow. So this is I think the most exciting thing about cloud native geospatial. And I have a message for you all, which is I want you to all stop thinking about files. Don't think about files. This is an example. This usually gets a few laughs from scientists in the crowd because they know what they're looking at here. They're looking at their working directory. It's like they threw up on a hard drive, right? And then they go and they publish this, and then they get hit by a bus, perhaps. All right, that's a little dark. Somebody looks at this hard, and they're like, what was this final version of the data that was published? What was this? Was it final class 2? Was it final version class? Final version final? Must be final version final because it has the word final in it twice. So we can create workflows now based on metadata. So when you write a function, when you write something, don't have it operate on files. Write it to metadata. So we have our workflow. Rather than the data going in, metadata goes in. This is really a simple concept, but it's powerful. That metadata is a complete characterization of the data. It has everything that we need in terms of the metadata, but it also has the location of the data and how to access it. When we output data from our workflow, we output metadata as well, including any new assets and the location of those things. Now, the advantage here is we can easily track data provenance. We can insert into this metadata what we had done to it. We can put the source of the data. In Stack, we use this derived from link, and it points back to the source of the data. And we have now a complete record of what was done to the data. It's a really simple but powerful paradigm. So in short, like to say that cloud native geospatial, even if you want to build services, it really is the foundational architecture for this concept of a queryable Earth. It's the foundational architecture for which you should all be building geospatial software. If you want to build services on it, that's great, but also don't discount just giving your users direct access to the data. They'll build cool services. They'll build the things that they want on top of that. And that's it.
So Brianna's next.
Okay, good morning, everyone. My name is Brianna Pagan. I'm at NASA Justice, and I'm just going to keep building off of Matt's presentation and dive a little deeper. I can't go too deep. It's only a 7-minute presentation, but I think it's really common for us to throw out all of these new acronyms and assume that everyone knows what we're talking about. So I'm just trying to orient the session a little bit more and dive into cloud-native geospatial formats. So the motivation, which I don't think I have to spend too much time with this crowd going into behind this, is obviously our archived amount of data is exponentially growing. So just looking at this EOSTIS example, by the end of this fiscal year, we would have about 62 petabytes in storage. And by the end of 2029, that should increase a tenfold to over 600 petabytes. So that volume of data is obviously very impractical for researchers to just download the data if they want to do any sort of timely analysis. Thanks. And obviously this is beyond EOSTIS, right? We see a boom in just satellite industry as a whole, and we see more and more private companies starting up and also trying to become more vertically integrated. And what we mean by that is they're not just accessing and providing data, but they're also trying to provide data analytics, data processing tools. And it's not just limited to satellite data. When we're talking about geospatial, I mean anything from airborne missions, UAVs, and even information that we collect from people's cell phones. So to make sure we're all on the same page, what's the definition then to be cloud native geospatial? This means just standards and software that are built for the cloud from the ground up. And I've stolen some principles from Chris Holmes on what makes cloud native geospatial important. And the first one is that it has to be read oriented. By that, I mean some sort of performance that allows us to run things both in parallel and allow accessing to just partial components of a data set. It should also be convenient and compatible with existing tools and also focus on some optimization of compression. I would also say one of the most important parts is making sure the data is available over HTTP and has interfaces for things like S3, Google Cloud Storage, etc. On the theme of this conference is making sure that this data is available via open source, and also that there is multi-scale metadata. And what I mean by that, I'll use Stack as an example, where I can search for information and search for data either by its item, a collection, or an entire catalog. So I'm going to go very quickly on just what are our most common geospatial data formats and what's this cloud-friendly version of them. So the first one, we'll start with a raster. Raster is typically some snapshot in time gridded data. You can think of these as DEMs or just multi-band single date satellite acquisitions. We're used to working with these in GeoTIFFs format, and the cloud-friendly version is aptly named COGS, Cloud Optimized GeoTIFFs. The nice thing about COGS is they abide by OGC standards, but there are additional restrictions to make them perform in a cloud environment. And there's two aspects of this. Matt touched on one of them, and it's really the philosophy behind anything being cloud optimized. And that's if we have some sort of gridded data set, we want to be able to chunk that data set in a meaningful way. That way, when I want to select a certain area, I can very quickly map the corresponding chunks and access the data quicker. The other arm of that is being able to do overviews, and this means being able to visualize data not in just the native resolution of 10 meters, but also being able to scale that, looking at the whole world, maybe at a lower resolution, for example, 10 kilometers. Lastly, I want to say a true COG is only when it's available on a server supporting HTTP request. And again, that's true for any cloud optimized data format. So building on raster, we also have multi-dimensional rasters. These are data cubes, typically in time. We can think of weather forecast data or climate reanalysis data. We're used to seeing this data in netcdf formats or HDF5. And the equivalent of this in cloud is ZAR. So ZAR is an open source specification for storing chunked, compressed, n-dimensional arrays. There's ongoing efforts for standardization via OGC also for ZARs. And because it's n-dimensional, it's not just something specific for the geospatial community, but there are extra efforts of things like Geospar specifications that help us also orient how we use ZARs for geospatial purposes. The next example I have is vector data. So this is data stored in columns, and that would include lines, polygons. An existing data format example of that would be shape files. The cloud-friendly version of that is GeoParquet, and GeoParquet defines how we store that vector data in Apache Parquet. And similar to COGS, right, it's going to be supporting efficient filtering and chunks, subsets of the original column data, which allows us to partition data into different files and enable spatial indexing. The last format, very briefly touching on, are point clouds. So point clouds are just a set of data points in space. We can think of this as the information coming from LiDAR measurements. The existing file formats is .ply or .xyz. And another aptly named cloud-friendly version of this is just cloud-optimized point clouds, or copc.io. And they have their own geospatial cloud file format, the LAS zip. So I want to touch a little bit on which format do we use and when. It's a question I hear a lot in conferences. It's a question I asked myself. And first, I want to start with the whole idea of pitting these spatial formats against each other is the wrong framing. So I hear a lot of, should I use a COG or a ZAR? That's very use case dependent. Right? If I'm trying to visualize data, I'm probably going to want to use a COG. If I want to do long-term time series analysis, I probably want to store my data as a ZAR. There is an ongoing comparison paper that is led by Vincent Sarago. You can add to it. We're looking also for use cases to add to this. And one of my favorite quotes from Howard Butler is that there's actually no ideal cloud format. Rather, they are extensions of formats which allow spatially accelerated reading over HTTP. I wanted to present one justice use sample, but my colleague Hailing will go in a little more detail later. But again, when we're talking about what is the ideal way to store the data in which cloud optimized format, it really goes into a lot of factors, including what your end user needs are. So how much local storage are they dealing? What are our egress costs? This is just one example from one of our data collections. Again, Hailing will go in more detail later. I want to end maybe with some grounding. I can't take any credit for this. This is coming from someone from Ryan Abernathy's lab. And I couldn't relate to this more. I was definitely that person carrying around a suitcase of Seagate drives with like 12 terabytes of data. And I think, everyone in this room, we're very forward thinking. We're trying to understand what's the best way, but we also have to meet people where they're at. And I think for a lot of end users, especially academics, if you give them a way to bulk download data, whether it's in cloud optimized format or not, they're going to choose that. So I hope also part of the session we can brainstorm better ideas of how to educate the community. And with that, thank you for your time and looking forward to talk later.
Okay, so we do have time for one question if anybody has a question for Brianna, or we can leave it to the discussion topics. So I think Christine is next.
Which one were you? Which one were you?
I'm the one labeled Christine.
Oh, sorry. That's all right.
It's the PDF.
Oh, yes. So it'd be this one. Clearly, I've captured my mouse somewhere. share my screen. And let's get Zoom out of your way, because that's a lot of Zoom to look at.
It is. It's kind of blocking about half the slide.
All right, Zoom.
Thank you.
Not a problem.
Okay, so my name is Christine Smith. I work at NASA's Desk, and I'm going to be talking about metadata for geospatial multidimensional XAR arrays in the cloud, which is an awful lot of words to get through in 7 minutes. So we'll see. Okay, how do I advance the slides? Yeah, the arrows are not working.
Click into it once.
Okay. But strangely, I'm actually going to start with like why XAR, because I think some people have used XAR and they love XAR and they're going to be very bored for the next 2 minutes. But I run into a lot of people who haven't actually tried it. They've heard about it, but they haven't actually like looked at an actual XAR. So I'm going to start with sort of a journey. So this was the journey in edited form that we had. And it may look familiar to some of you who have also sort of moved into the cloud. So sort of the first thing you do is you say, I have this fabulous data. It's in HDF. I love HDF. I know how to use HDF. I'm going to copy it into S3. I copy it into S3 and I'm like, oh, I'm in the cloud. I'm there. I've done it. And then I say, okay, there's this fabulous library. It's called S3FS. It means that I don't have to worry about S3 because I'm going to make it look like a file system. And so now on my computer, I take all the code and everything I already know, and I run it against S3FS, and I access my data, and I am in the cloud. It's great. And then the first time you do it, you're like, oh my gosh, that was terrible. Like, what happened? I thought the cloud was supposed to make everything fabulous. And so you look at it and you say, oh, I got it. It's S3FS. I should be using Boto3 because that's the native library for accessing things in the cloud. I shouldn't be using this S3FS because it's fooling me. The cloud is different, S3 object access is different. So I put in Boto3, and then I need to write some more code because Boto3, it is a different interface. And then, I look at it and I say, well, actually, I actually need some like extra metadata that I need to put in the cloud now in order to, finally get this sort of better performance than S3FS. And then you look at it and you say, maybe, you say to yourself, why am I still fighting to use formats that were designed for disks and work really well on disks, but weren't designed for S3, which is really a different way of storing data? So I did all of this work. I do get better performance than S3FS, but maybe this isn't where the journey should end. And then you sit back and you think to yourself, all right, what am I going to do next? And then maybe you step back and you say, okay, well, what am I actually trying to do? What is important about the data? Is it the storage model? I mean, I love HDF, I'm familiar with HDF, but is it the storage format that matters, or is it the data model, right? The data model is what allows me to store the kind of data that I have. And so maybe at that point I say, actually, the storage format itself is not what's important in terms of me being able to express my data. It's the data model that matters. And then at that point, maybe you run across XAR and you say, oh, hey, this was inspired by the HDF data model. It lets me store these multidimensional arrays organized in groups with metadata, looks very similar to HDF. And crucially, it was designed from the ground up to work well with object storage. So it does all that heavy lifting for me in terms of performance. So I do want to mention some related technologies that you're probably going to run across if you've dealt with XAR. So one of them is Xarray, which works really beautifully with XAR. And Xarray, I'm not 100% sure, but as far as I can tell, Xarray was the first one to sort of add metadata that kind of added that NetCDF data model concept to XAR. And then hopefully you'll also run across the fact that Unidata, and this is a little bit of a work in progress, is adding ZAR support in other languages. So ZAR is no longer a Python thing. You're actually getting support for it with the NetCDF-C and NetCDF Java libraries. So if you Google, or at least if you Google the way I did, which was apparently not terribly competent, but if you Google for the ZAR storage specification in OGC, there was a version that came out last year. And for me, that was the one that was at the top of the Google search. But it turns out there was a version that came out this year in April. And so in addition to having the kind of metadata that you would expect in the standard for like data type, array sizes, chunking, it now includes some additional metadata, an underscore array dimensions, which adds that association between array dimensions and variables like you have in NetCDF. And it also starts talking about adding coordinate reference systems, which of course is great for our geospatial data. Now, I love the line, the forthcoming GeoZAR spec should seek to reconcile these discrepancies in CRS encoding in ZAR, which I take to mean that like, we're hoping that somebody will land on one spec rather than two for doing this, but it's a little bit of a work in progress. So I want to like actually show you what this metadata looks like. So in ZAR, all the metadata is in JSON, which is very nice. It means you can just like download it and take a look at it. So this is the array metadata for a particular variable I created. It has chunks, it has compression, it has the data type, it has the shape. The sort of parameters should be very familiar if you've used HDF. And then these are the attributes for it. And so that first section, array dimensions, that says, okay, I have this 3-dimensional array and the names of the dimensions are time, latitude, and longitude. So I can go elsewhere in the ZAR store if I want to and see if there's some variables called time, latitude, and longitude. And then underneath of it, some of that should look very CF1-ish for folks who are familiar with the CF1 metadata. So it's extremely easy to take those CF1 conventions and map them into ZAR. Okay, so this one, I'm hoping this blows your mind because you haven't actually tried it. You probably can't see it, but this is me running NCDump on a ZAR store, okay? And it looks just like running NCDump on like an old NetCDF3 or NetCDF4 file. And I think the point here, right, is that the folks who defined the NetCDF standard, when they were looking to go in the cloud, they said, you know, how do we take our data model and put it in the cloud efficiently? And they said, aha, ZAR. So just as they changed to HDF5 when they went to the NetCDF4 standard, they're now looking at ZAR as a cloud format because they recognize that the thing you want to really maintain here is the data model, but the storage format can change underneath. Okay, and I guess that's the end if anyone had any questions.
Any questions for Christine? Great.
Sorry, Ken. Apologize in advance. So everybody's mentioned metadata. Fantastic. I really do think that's fantastic. Our metadata standards are linear, but metadata are fractal. And until we change the way we're thinking about how we standardize our metadata, we will never be able to get to a point where we can actually use it across multiple data sets, multiple time series, multiple uses. It'll just not happen. So we have to change the way we're thinking about our standards. But thank you very much for setting up that question for me.
Right. Well, I mean, you know, metadata is an ongoing issue, right? And you can have metadata that works to solve certain problems, and it's still useful even if it doesn't solve all problems. But yes, I mean, we could spend weeks talking about metadata.
All right, Heiling?
Oh, didn't want to press that button. Sharing screen 2, slideshow, and beginning. Oh. Oh, you're over there. Which computer are we on today? We're looking good, Sahara, online? Awesome. Why do I not see it? Sometimes you have to switch it back and forth. There we go. Awesome. And we look good, Sahara? Awesome. Sorry about that.
No worries. So,
Oh, no, we are looking at percentage. Sorry. No, we just need to share the right one, which is currently my gross face. Boom. Awesome. My apologies, folks.
I'm a troublemaker, sorry. So, where's the cursor? Oh, there's no cursor, and if I want to go back and forth, how do I go back? Where's the cursor? So, this doesn't work, so I have to click.
Do I need to actually click?
No, I have to click.
Oh. No, it should be going.
Oh, it's working now.
Yeah.
Okay. Okay, perfect. Okay, thank you. Hi, morning, everyone. This is Hai Liang from Geospatial. Actually, my presentation may be a little bit boring because it's really a method for fast and cheap high-resolution data analysis in cloud. Okay, which is called ZAR-based chunk-level accumulation in reduced dimensions. First, a little bit background. At Justice, we have a data visualization service called Giovanni, which is mostly doing averaging for level 3 data along one or more dimensions, which is, this is very simple, but it can be very expensive for high resolution data. So it can give lots of pressure to our server. So this is a key thing we want to address when we started our cloud migration a long time ago. And during the migration, we were actually not only looking for some format that is cloud friendly, we're also looking for some algorithm to make things fast and cheap. Because in cloud, as you know, everything comes with a cost. So you can have many instances to make things very fast, but we want both fast and cheap. So we first introduced a method called multidimensional accumulation, which is actually very straightforward. So basically, when the new data arrives, instead of saving its original value, we're going to be saving its volume integral or running sum from the origin, and we call it accumulation. By doing that, for example, if we want to do a area averaging in this bounding box, with the accumulation, instead of looping over each single point inside, we just need to grab a few points at the corner and do some very simple linear combination. We have the results, which is very cheap, but this method can be very expensive for data preparation because it's a high dimensional integral. Of course, we can argue this is just a one-time thing, right? We just do it once, but the user may still not be happy with replacing the original data by the accumulation values. So later, we were able to improve this method after we decided to switch to ZAR as our storage backend in cloud. As you know, ZAR data is divided into chunks, which is smallest data transaction unit. And in general, each chunk will have many points inside. So it's going to be nice if we can just do accumulation from the starting point of the chunk, which cover everything before it, and don't worry about any other points inside the chunk, because we need to load and decompress the whole chunk in memory anyway, right? So this is some details, like how do we prepare accumulation data for ZAR. Sorry, we don't have time to go into detail, but basically the idea is that for each point on the leading geometrical elements of the chunk, we're going to do accumulation along its complementary dimension. What does that mean? So, for example, for the points on the leading, sorry, I don't have the cursor. Cursor doesn't show, I think. Okay, but for the points on the leading XZ plane, which is highlighted on the second box, so we just need to do accumulation along its complementary Y dimension. Okay, so in that case, like we are not only doing accumulation for less data points, we're also doing it in reduced dimension, which is 1D in this case, and it's embarrassingly parallel, so it's going to be very fast. And after that, we also want to do the two-dimensional accumulation along the leading edge of the cube, which is a higher dimension, but it happened for even fewer data points. And finally, you may also want to do a three-dimensional accumulation, which is expensive, but it only happened for a single point. As a matter of fact, in Giovanni, we never need to do that because Giovanni, we currently don't have any averaging service that's gonna do average along all the dimension at the same time. So, okay, so with the accumulation, we can provide fast averaging service. Similar as the original method. So instead of looping over all the chunks inside the bounding box, we just need to grab a few chunks as a corner. The only thing is that we need to reorganize those chunks into a what I call a composite chunk, which is a mixture of the original and the accumulation value along certain dimensions. I have this generic workflow to automatically build this composite chunk for you based on the averaging dimension you provided. And once we have this chunk, you can simply add up all the value inside this single chunk, which is going to be equivalent to adding everything before it, including this one. So again, we don't have time to go into details, but if you are interested, you can refer to my AGU presentation from last year. So by using this method, we did some benchmark on the our high-resolution GPM data in AWS by using Dask cluster. As you can see here, this accumulation is really not touching the original data. It just introduced some very small amount of extra storage, which is 5%. And this accumulation is going to finish like an hour for the whole 20 years, and which is going to be very fast. And with this very little overhead, we can have dramatic performance improvement. For example, like for the global averaging time series for this GPM data, on-prem is going to take about hours or days or even not possible. But with this ZAR accumulation, we can have it done like seconds or at most 15 seconds for the whole 20 years by using very few small instance, which is very cheap, again, because we are just grabbing a few chunks instead of all the chunks along the averaging dimension. So, so to summarize, so this ZAR-based chunk level accumulation in reduced dimension method provides dramatic performance improvement with very little data preparation overhead and with very minimal cloud cost. It is also very flexible. For example, if you think this 5% extra storage is still too much, you don't have to accumulate every single chunk. You can accumulate every few chunks that can make things even even faster, but the performance may not be super good, but still going to be much better than without the accumulation. Again, with a little help, we have a very dramatic performance improvement, and they are tunable. And finally, they're also numerically very stable because things happen in reduced dimension. The chance of the data overflow is very low. So I think that's everything. I'm not sure I ran out of time or not, but any questions? Thank you.
Any question? Okay, great.
Very cool thing you just presented. Isn't it conceptually similar to like what COG does with storing overviews, right, which are sort of just averaged, but in a sort of regional way? So can you talk about the relationship between this and overviews?
Yeah, I'm not exactly familiar with, I know I have a high-level concept of the COG overview, but basically in Parquet, like probably similar, they have like each page or like and they have some statistics about the data, like the mean, or the sum, or even the standard deviation of everything inside that single unit. But this method is actually, has some information that's not covered by the standard, this kind of information, because it's really just like showing the running sum before it, instead of any statistics internally inside this single chunk, for example. This is something unique, but it only apply for the data which is aggregatable, along those dimensions, right? So, yeah, so that's a key difference, I think. Thank you.
Awesome, thank you so much. So Maha?
Which one is this? Should say Heg Day. Yeah. I thought it was. Sorry, I'm learning names.
So what do I use to?
Left, right.
Good morning. I'm Mahaval Hegde. I'm with NASA Geospatial. So my team presented a rosy view. I'm here to give a little bit of a pessimistic view, and hopefully we can find some solutions to address it. So I'll be talking about, mirror data stores, what are the challenges and possible solutions. So for this talk, basically, mirror data store is something that is derived from the authoritative source. And along the way, the data might have been stored in a different format than the original. It might be hosted in a different location, or it might have been transformed where the data values actually changed. So the rationale for these mirror data stores, so essentially, it's something that provides data access in a format and location that's actually friendly for consumption. So, you already saw some evidence of this. They all generally provide better read performance, which leads to faster analysis and better user experience. And even for a data center, it will probably save labor costs in developing services because there is no overhead of data wrangling and things like that. So that's all great, but there is no one-size-fits-all solution. So most likely, each usage pattern probably will require a different way of organizing data. So hence, essentially, we end up creating copies of data. So what are the challenges of creating and curating these data stores? So the common, I guess, the concerns from a consumer is, is this data copy from a trusted source? Does it have any reliable provenance? Is the data, verified, or can it be verified? I mean, is it verifiable? Is the data complete? Does it have missing records? Has were the values modified along the way? And obviously the other questions related to licensing and how to cite the data. So even if you can answer these questions, how do you provide the evidence of these things? Where do you provide them? So the classic case is, some entity, they acquire the data from its official source, they reformat it to fit their needs, they publish it to open catalogs. I guess in the era of open science, this is going to happen more often, and then they move on to other interesting things, and we have a dangling data store basically. I mean, this is already happening. Last year, I think in some other session at a different meeting, Nick Doty from Estes, I think might be in the audience. He was looking at a Muir data store, which pointed to two basically buckets. They were supposed to be the same data. One was the original, another was reformatted, but amongst themselves, they actually differed. So this is real. So basically, and it's going to happen more often, people are already doing it, because as data centers, we don't provide data in a cloud-friendly way. So we start with something original, and then somebody starts putting data which which fits their need, but it looks like an authoritative source, but it may not be maintained. So mirror data stores is not a new concept. We already are familiar with mirror sites. So everybody does it in other sectors. So why can't we do it? So when I go to Home Depot, I buy a tape. I don't care whether it's the exact wavelength and measures whatever the speed of light. I just buy it, and it works. So the only difference is in those cases, basically there's a traceability of comparing all the way back to the original or the highest standard. So maybe if we can do it, we can operate these mirror data stores better. So going back into the details, there are some key characteristics for what is a trusted source. So one of the key things is to ensure the integrity and authenticity. So, and there are some standards and certifications. I think most of the Earth Science or Earth data archives, I think they comply with this core trust seal. So one way to sort of, advertise it is to, basically display these accreditations and how we comply with them in a very visual way. The next is the provenance. So basically, for the earlier examples that my colleagues were explaining, Giovanni is an application. It uses ZAR as the data store. We thought of storing some minimal information that indicates what process it went through, what was the input, and the time when the input was sourced, because the input data can change, so that way we know, whether it's fresh or not. There are some standards, which we can consider. I like the processing graphs. That's from OpenEO. And Prov has been there for over 9 years. I don't know about its, I guess, the usage, but there are some standards to consider. So I say, what happened? So basically, one of the things that we decided was to embed provenance in the data store itself as metadata, so that anybody who is accessing the data store can see it and easily read it. So the next one is the verification of the data store. So the question to answer is, does the data contain the right numbers? Which is a difficult thing to answer because of the size of the data stores in our case. So the possible candidate best practices might be, we provide some checkers, just like what we do with unit tests for code, and have these data stores frequently verified and prominently publish the last verification time. So the next challenge is the completeness. So this is basically answering, does the data store contain everything it's supposed to contain? So some of the practice that we can consider is providing metadata about freshness, when things were last updated, and provide some completeness checkers so that even users can verify these things. So technically, at least on paper, so from the provenance, we should be able to trace it to the origin and compare using, the metadata that's in the provenance, including, things like hashes, things like root hash of the input data. I mean, these kind of things are already in use in things like blockchain. So we should be able to do that for our data as well. So transformation itself, we can use the provenance, and for licensing citations, there are existing metadata in the registries that are out there. We should continue to evangelize, using DOIs. And essentially what I'm looking for is, any interest in this computing cluster at ESIP to standardize and come up with these, guidelines and best practices. So we're going to try throwing open these ZAR data stores to users because it helped our application at Justice. So it's going to be done anyway, so help us. Any questions? Thank you.
All right, thanks so much. So our next presenter is Ramon, who is virtual. So I think we can switch, or
Ramon, can you hear us?
Yes, I can hear you. Can you see me?
Screen share over us.
I can screen share, no? Okay.
oh, great.
If I can find it, yeah. Let me see. Okay, can you see my screen?
Yep.
Okay. Yeah, sorry I couldn't make it over there, but I have to go. The kids are in camp and it was hard for me to do it. So what I'm gonna show is not so much focus on data exclusively, but on infrastructure. So I'm Ramon, and the co-founder. Can you hear me okay, or is there echo? I can change the mic.
No, you're fine.
Okay, perfect. Yeah, so I'm Ramon. I'm the co-founder of Nateca. I'm also currently working with Dan Duffy on the Science MCE, on the Science Managed Cloud. I'm going to present what we did for the Earth Information System pilot back a few months ago. Let me see. So basically, this is the infrastructure that we deploy for the Earth Information System. So it's kind of like a labyrinth. But basically, it was an infrastructure that we co-designed with the scientists, the data scientists, and the DevOps in the cloud. I mean, it was based on Jupyter Hub. So we have an infrastructure where we basically deploy Jupyter Hub, DAS Gateway, as you can see here. But then we added some features like storage features and other type of features that the scientists were using during this pilot project. So the main thing is we were working with 3 different groups of scientists, one that focused on fires, another that focused on sea levels, and another one that focused on flooding. We started deploying one of these infrastructures, and then it was very successful, and right now we have like 30 different we call it DAS Hub. So we became really good about deploying this infrastructure. We can deploy the whole thing in less than an hour. The main features of this infrastructure is that you have access to S3 directly from your notebook. You have access to a network file system where you can have your data, and you can also have access to a local file system. As I said, the infrastructure comes with a DAS, with the capability of deploying DAS cluster very easily through a user interface or through Python. It's connected to an HPC server, and this is something unique that we do. So basically, we let the scientists deploy HPC clusters in the AWS cloud using the AWS tool called pCluster. And then we also have connections to a Git repository. And then we have added some features that are unique to the Science MCE that are not currently available on the Jupyter project. And those features are the S3 Plus, the S3A Plus, which basically it's a Jupyter Lab extension that allows you to connect any bucket that you have access to connect it to your notebook. And you can do it through a user interface. You just have to put the name of the bucket, and it will show up in your list of buckets. But it also allows you to explore the different public data sets that are available. So for now, we support the AWS data set. So as you know, they have plenty of data sets that are public. So you can browse them and add them to your notebook, and then start accessing from there. We have also added a feature called API Baker, which is now in proof of concept phase, but it's already being used by several groups. And API Baker basically is a Jupyter Lab extension that allows you to turn any notebook into a service endpoint, into an API endpoint. This was very useful because we have several scientists working on problems that were similar, like turning SAR into cloud optimized GeoTIFF or NetCDF into SAR. And there were several groups working on the same algorithm or same scripts at the same time. And then we realized, well, why don't we let somebody do it, whoever is the best doing those things. And then we turn that notebook into an endpoint that he can share with the rest of the group. He can even use from a website or from a collaborator. So we have that Jupyter Lab extension, and it allows you, as I said, to turn any notebook into an API endpoint. There is also somebody in the GML group using it because we have built an air quality with bias correction model, and he wanted to figure out a way to easily create an endpoint for that model to share with his collaborators all around the country. So he was able to do that with this extension. And then we have another extension that uses the Voice Atlas natural language processing software. Basically, it allows you to connect your notebook to a source of knowledge. It can be maybe knowledge about the data set that you are demonstrating or the research that you are demonstrating. And the users of your notebook or the community that look at your notebook can engage with that research or with that knowledge in that notebook through an intelligent chatbot. So this is the software stack that we use to deploy these systems. As I said, we started with just one one of these systems for the James Webb Telescope. And then there was the Earth Information System project that required 3 more of these systems. And now, as I said, we have 30. So what we have done is we have gone to start using Rancher, which is an application that uses the Open Cluster, the Cluster API, I mean, for Kubernetes, and allow us to administer all these clusters with a single point of view. Then we have other services like Dask Gateway, which come from the Jupyter project, and Zero to Jupyter Hub. And then we use all the AWS services to deploy the different Jupyter app extensions that we're building, like AWS App Runner, Lambda, that sort of things. So, and I think that's all I've had. I don't know if you have any questions.
Any questions for Ramon? Okay, cool.
Thank you.
Oh, we do have a question. Great.
Yeah, Ramon, this is Rich Signal, USGS.
Hi, how are you doing?
Hey, you have a fair number of those deployments, right? Could you give us an idea of like what some people are doing with them?
Yeah, absolutely. So, like for instance, we have somebody in the JPL in a JPL group, and they were using it to to run some of the models, doing some troubleshooting of the models that they are developing. There is another group. I think this was part of Alexis group and Alexis Shiklomanov at NASA, and they were building notebooks that the community could use later on to learn and to contribute to the open science approach. Some other groups, what they are doing is they're building the science on the notebooks, and what they want to do is then create links to those notebooks on their website. So basically, they have a website that explains the research that they are doing, and they want to be able to share the notebooks on their website so the community can explore the data and the research themselves. So that's some of the projects that they have been doing. And of course, you can always ask Alexei. He's more in tune with the scientific side of the infrastructure. Thank you.
Yeah, Rich, I can talk to you after, actually. I know a little bit about Alexi's projects. All right, Terrence, you're up.
Thank you.
Thank you, Ramon.
Thank you.
Gotta switch screens just to refresh it, make it think it knows what it's doing. You are my boss. This was working so well. Classic IT, have I turned it off and on again? Yeah. It's embarrassing how often that actually works. Maybe I'll enable editing. Bringo Brango. And now we need to actually show, oh. Is this where I start dancing, Rich? Start the party? It's still going so well. It's all right, I have faith.
If there's any questions before my talk, take them now.
Now would be a good time if you have any discussion topics to add them to the discussion topics document. Are we there? Oh,
I apologize, folks.
never mind. Please have your attention to the front of the room.
See if I can
Terrence.
change slides here. Excellent. All right. Good morning. My name is Terrence Stohinanshu, and I'm a senior software engineer at Azavia. This talk is about the work we've been doing with NOAA's National Water Model, trying to make it more accessible over the cloud and benchmarking different techniques. For that, I'm grateful to be here. I've learned so much from, and all the ideas that I've seen here will inform our work on this project and others going forward. Azavia is a Philadelphia-based B Corporation that works on advancing geospatial technology for civic, social, and environmental impact. We've made significant open source libraries like GeoTrellis and Raster Vision, worked on a number of open source projects like Model My Watershed and District Builder, and do custom cloud-based geospatial software development at the regional, national, and international scale. Our interest comes from a NOAA Phase 2 SBIR grant, which is centered around advancing the utility of the National Water Model to support flood extent delineation modeling. One key aspect of utility is ease of access, and by improving the cloud-based performance of NWM, we can rapidly deliver flood inundation maps, ease the collaboration between the National Water Center and the regional forecast centers, and even start to build on top of NWM with techniques like machine learning to support decision-making. The National Water Model is a hydrologic modeling framework for forecasting stream flow over the entire continental United States. The reanalysis dataset, the version 2.0 of it, is a backrun of the model on existing data, a 26-year retrospective simulation that provides historical context to current real-time conditions. These runs are stored as netcdf files, 2 for every hour, 2 every 4 hours, for a total of 24 files a day. And each file is a state of the entire country at that time slice. Now, most people are concerned with a particular region over time, not the full country at a specific moment. Currently, this requires downloading a large amount of data and discarding most of it, except the parts that you care about, which is slow, inefficient, and expensive. Ideally, users should be able to specify exactly what they want and get just what they need in a readily usable format. The question that we're all asking here is, can we improve performance by using cloud-native formats? And the answer, of course, is yes. NWM is already available in ZAR in addition to netcdf, and it does allow cloud-optimized querying. And PangeoForge provides a platform, a repository, and a toolchain for converting scientific data into cloud-optimized formats. So now the question becomes, how can this be done well? This is where industry experts like Azavia can help narrow the technology gap between subject matter experts and the tools and techniques available at their disposal. The focus of our work is to compare a few different options and share our recommendations. Our approach is to identify typical queries to benchmark, convert the dataset to a number of cloud-native formats like ZAR and Parquet, try different chunking schemes, and measure the performance. These benchmarks will be used to make recommendations, and the code and datasets will be released as open resources. Now, this is a work in progress. We're in the process of learning about these datasets, formats, and libraries. In particular, we've struggled with writing and reading data files in Parquet efficiently using Dask, which is a Python library for parallel processing, already mentioned. We've talked about ZAR a bunch already, so I'm not going to go into too much detail. It's multidimensional, great for climate data. Parquet, people are also familiar with that. It's great for read-optimized tabular data. A typical query, when we say, is something like the mean stream flow in a Hugate. So here we have 3 variants. One is the mean per stream per day, one for all the streams in a Hugate, for example, per day, and one for all the streams per week. And we're running this on a month, a year, and a decade of data. To test the data set, we made a subset of the NWM with 10 out of 26 years of data and 1 out of 21 HUC2s. These are all the streams for which we have 10 years of data that we'll be querying. We also got COM IDs per Huckate from the NHD Plus dataset, and we stored everything on S3 so that we're not using a database in our work here. The reanalysis data set has many components. We're focusing on the stream flow, which is a time series for every stream reach, which is essentially a tabular data set. So we can use the NHD extracted streams per Huckate stored on S3 to connect the geospatial Huckate to the stream IDs. And then this tabular data set just has the stream ID and the time series. Given that this is a tabular data set, we hypothesized that Parquet would be a good fit. Our subset is about 1% of the total reanalysis data set. And we're running this on, and we are reformatting the data sets. So we have the original chunk-shaped ZAR. We also have the transposed chunk shape, which we hypothesize will be more efficient for time series queries. So it's the same data, just chunked differently. And we have Parquet, which is made via the DAS data frame. We're running this on DAS Hub, also already mentioned, which is basically a cloud-based environment that combines DAS Gateway and Jupyter Hub on Amazon EKS, their Kubernetes offering. This allows us to spin up clusters on demand and execute these highly parallel workflows. On the right, you see a screenshot of the DAS Diagnostic Panel, which shows the workers in real time. And here are our initial results. There are 3 charts, one for querying mean stream flow per feature per day. So that gives us the average flow for every stream every day. The second one is for mean stream flow over the entire Huckate per day. The last is mean stream flow over the entire Huckate per week. The y-axis is runtime, goes from 0 to 35 seconds. We have 3 time ranges per query, a month of 31 days, a year of 365, and then a decade. The blue bars are the original chunk shape, and the orange bars are the transposed chunk shape. These results indicate that for large time series queries, using the transposed chunk shape is better and can provide a speedup of up to 5 times. And here are the ZAR results compared with Parquet. We focus only on the third chart from the last slide. The mean flow for all streams per week. The green bars are Parquet runtimes, blue the original ZAR, and orange the transposed chunk ZAR. The y-axis now goes from 0 to 100 seconds. The Parquet results are surprising. We expect them to be roughly comparable to ZAR runtimes, but in fact take much longer. It's interesting, though, to note that the Parquet runtimes do not vary significantly between small and large-scale queries. We suspect that there are issues with the way we're writing and reading Parquet via Dask. If you have any ideas, please come find me afterwards. Our next steps are to improve Parquet performance, run larger scale experiments, benchmark with other queries, use this knowledge to save the entire NWM in different formats, and also develop a data access library that automatically selects the best format given a query. If you have ideas for other relevant queries against this data, please come talk to me afterwards. We are in good company. The USGS has been thinking along these lines for a few years. There's great discussion on the Pangea forums comparing these formats. The Pangea Forge, of course, has making great progress standardizing ETL for scientific data. And there's projects like Kerchunk, which allows ZAR-like access to netcdf files directly. It's our privilege to be a part of this curious and brilliant community. I'd like to thank the entire project team at Azavia, my colleagues who've made excellent contributions, and to our advisors and subject matter experts for their invaluable guidance and support. All this work is open source and available on github.com/azavia/noah-hydrodata. If you go into the source ESIP 2022 presentation folder, you'll find all the notebooks used for the experiments in this presentation. Thank you for listening to my talk. If you're interested to learn more about us, please find us online at azavia.com and at Azavia on most social platforms. We believe in open source, open data, and open communication, and welcome all conversation and collaboration. If you're interested in working with us, we are hiring. Check out our careers page. Thank you.
Any questions for Terrence?
I think the one interesting thing, well, one very interesting thing about the whole Kerchunk thing was that we, at least in my head anyway, it was like, okay, yeah, like somebody mentioned earlier, like the format doesn't matter. It's like the chunk shape and the chunk size and the compression, and you guys showed that with your different, making the chunks orient differently, and time series was much better. when we compared Parquet to ZAR with the exact same chunking, I was surprised to find out that Parquet was a little faster. But it was, so I think actually Parquet is a great choice for this because Parquet is available and it's more widely usable in applications than ZAR at this point, right? But ZAR was still very fast. It was like, they were both very fast. And so I think the lesson, I think it just basically confirms that, yeah, it's all about the chunk shape and the chunk size more than the data format, but for performance, for read performance.
Yeah, I
agree
think
with
that I agree with that. I think one of the things we've observed is Parquet, at least reading it in pandas, is better suited for memory-oriented environments when you can load the whole data into memory. But that's not always possible when you have a larger data set, and that's where reading via DAS data frames comes in. I'm curious to see what we find once we improve our DAS data frame read and write performance with Parquet, if there is significant difference. But I think you're right, that it is more like the shape of the data than the libraries. Parquet is more popular and more people know how to use it. So it might be almost a matter of accessibility, that if the data is available in that format, then more people might be open to using it. All right, thank you.
Thank you so much. All right, Ryan.
If you don't have it open, it's fine. I just put Amy's name on it. There's a drive. Yeah. There you go.
Let's refresh it
Yeah.
and then grab.
Perfect. I'll offer a comment on the discussion that just happened while things are loading up. Performance is a function of the format, like the infrastructure, the network and the storage and the client libraries. And in particular, the client libraries are always in flux. And so performance is not static, right? We all have the opportunity to improve the performance of our favorite tool by really digging into the code. And that's where, upstream open source contributions can have a huge impact. ZAR didn't even exist 6 years ago. And so these things are very much in flux. Parquet and the Parquet ecosystem have a huge amount of business analytics software development driving its constant performance improvements. And we can do the same thing for our favorite file formats if we can sort of align and collaborate on that.
So I'm opening you up in a Edge,
Okay.
just so we can watch it explode. So you get.
I'm hoping to give a quick demo. So will I be able to open a web browser after this?
You should be able to
Okay,
drive as much
great.
as you want.
I'll try it. Okay, great, cool. So we're coming up to the end. I'll try and move fast. I'm really excited to be in this session and share what we've been working on with PanGeoForge. It's come up a couple times already, so I want to give just a quick overview of what PanGeoForge is, what problem we're trying to solve with it, and where we're at with the project. I want to acknowledge a bunch of contributors to this project, some of whom are in this room. And I want to thank the NSF EarthCube office for funding this work. So we've already seen several introductions to the idea of analysis-ready, cloud-optimized data, so I'm not going to spend a lot of time redefining these. I'll just kind of show you my slides. My favorite acronym is analysis-ready, cloud-optimized. Analysis-ready refers more to the metadata, the processing that's been done on the data itself to make it ready for analysis. And then cloud-optimized refers to the sort of file format questions of, is that data in a format that's readily accessible and computable on the cloud? And so, yeah, this is just rehashing things you've already seen, so I'll just move on. So the problem that we've, just for some context, through the Pangeo project, so I've been working on making analysis-ready, cloud-optimized climate data for 4 or 5 years now. Essentially, about 5 years ago, Joe Hammond and I wired ZAR into Xarray, and that's what sort of enabled a big explosion of experimentation with cloud-optimized climate data. And we've tried a lot of different things about making, different formats, creating cloud optimized data in different ways. And what we've concluded is that it's actually really hard to do this in a sustainable and effective way, right? So in order to make a good ARCO data set, you have to first have a lot of domain expertise. You got to know what's a useful data set, where do I find it, how do I clean it, what are the processing steps I might want to apply. Those require scientific knowledge. Then there's a lot of heavy-duty new technology involved in this. You got to know about, S3 and, all these formats, and you got to know about distributed processing. And then we're expensive. So these are expensive computations. So we're talking about many terabytes of data usually that we want to process. That costs money, that costs resources. And then finally, you have to be able to sort of validate your data set with analysis skills. And it's really hard to find one person who like has all of these skills and if you can find them, they're usually pretty busy. The question that we have been asking ourselves is, whose job is it to make this ARCO data, right? And many have suggested, the data providers should do this. I actually don't think so. I think data providers' job is primarily to provide, very well curated, reliable, and archival data, right? That's like a satellite provider. That's like their primary job, right? Scientists, users know what their ARCO data should look like. So in the PangeoForge project, we're trying to allow scientist users without necessarily a lot of technical background to produce their own ARCO data sets. That's what PangeoForge aims to do. PangeoForge is inspired directly by CondaForge. Just show of hands, who has used or interacted with CondaForge in any way in the room? Okay, so some people. I gave this talk at SciPy last week and every hand went up. So CondaForge is a community resource for creating Conda packages. These are software packages that can be compiled in the cloud and distributed. And what the CondaForge project did is it really democratized the process of generating these packages. Before, if you wanted to distribute a Conda package, you had to sort of compile the software yourself, and then you could just upload it to the web and put it into an archive. But most people didn't know how to do that. It was too hard. So CondaForge said, instead of actually doing it, just create a recipe for how to do it, contribute that in GitHub, and we'll make cloud automation take care of the rest. And we'll go and actually compile this software and upload it and do all that stuff. So we want to do that with data. That's what PangeoForge aims to do. And the project really consists of two main elements. One is something we call PangeoForge recipes, which is just a standalone open source Python package for building analysis-ready cloud-optimized data from some other data source. And you can go use that today. You don't have to use it in the cloud. You can just run it on your laptop or run it on your cluster and use it as a tool to build and manage data sets. Mostly focus on the sort of netcdf to ZAR style workflow, but with potential to expand. And then the other element is PangeoForge Cloud, which you can think of as sort of as a runner for these recipes that integrates with GitHub and produces these data sets, right? So where am I? I guess that's the end of my presentation. So now I'm just going to give a demo, right? So I think that's the easiest way to explain what this is. So now becomes the fun part of trying to use a Windows computer. Okay, so here's a browser. Okay, so I'm just gonna take you to PangeoForge.org. Okay, now this is our website, and what I'm gonna do is I'm gonna go look at some of these feedstocks, right? These are where the data come from. And I'm going to go click on one I created last week for demo purposes. This is the NASA Global Precipitation Climatology Project, GPCP, sort of a fundamental climate data set about precipitation. Who's interacted with this data set before? GPCP? Few people. Really great data set. So the end result here is basically, this is pointing to data in the cloud, right? that I can there's just Python code I can just copy and paste and load into a notebook. I'm not going to do that right now, but if you have a Jupyter notebook open with Xarray and Zar installed, go to the website and try it. You can just open this data set publicly anywhere. This is actually stored on Open Storage Network, which is a NSF sponsored sort of cloud style storage, S3 compatible storage layer. It's not in the commercial cloud, but it is in the broader cloud. Now, so where did this come from? Where did this data come from? This came from a, oops, wrong button. Okay, got to figure out how to open that there. This is linked back to a GitHub repository that's called a feedstock. Okay, and this feedstock contains some metadata about the recipe. So these are things like where did it come from? So someone earlier was mentioning provenance. So here we're explicitly tracking the provenance of this data, who generated it, who produced it, what's the license for it. And you can see that information appears here. So we have links back to those providers. By the way, NOAA should really actually provide an actual license, not just say no constraints on data access or use. If there's anyone from NOAA here, please actually license your data. Don't just say that. Okay, great. And then, so that's one part of this recipe. And the other one is the code. So you can see this is 31 lines of code, including comments and spaces, that describes how to sort of crawl the NOAA HTTP server, put together a list of files, and then turn this into an actual Zar data set in the cloud. What's that? Up a font size, sure. Okay, so, I'm not gonna walk through this code, but the point is, it's a relatively simple, few lines of code that just describe how I'm gonna ingest this data. And then by having this in PanGeoForge, we sort of have a link to that. We can see exactly when this was run. There's like a run that was, computed from a certain GitHub hash. So we have complete provenance tracking the whole way through of where this data came from. Now, the cool thing is now that this is in GitHub, we can start to discuss the data the way we're used to discussing code. So here's an issue I actually opened up. We found some corrupted data in this archive, right? So we found some bad values that were sort of like, there can't be, negative precipitation, right? So, we're discussing it, and we sort of debugged it, and Charles sort of went upstream and found that these corruptions exist in the original NOAA files, right? And so I said, this is why we need PanGeoForge. I emailed NCEI, and they blamed NASA. So they said, okay, well, we just got to, but the point is, like, this is happening in the open. We're talking about data and data provenance on GitHub, and the way we will fix this is with a pull request, the same way we fix software. So, we're open for business. If you want to understand how to contribute to this, we have documentation, and we welcome new recipe contributions to this, which are submitted via a pull request. Disclaimer, it's really janky at this point. This is like, it barely works. It kind of works. It mostly doesn't work, but we are working hard. This is a really hard thing to build, but I guess my message for people here is, if you're considering trying to put ARCO data into the public cloud, and you don't care about doing this behind some veil of secrecy or security or privacy, consider trying to do it through PanGeoForge, because then the community might step in and be able to collaboratively help curate and maintain those data sets, which, as we all know, is a lot of work. So I'll stop there. Thanks.
Okay, great. We have one question. I know we're over time, so I'm going to try and wrap it up. But
Thanks, James Gallagher, OpenDAP. That was a great talk. I'll try to speak quickly. So you mentioned the public cloud, you're using Exceed. How can other people get access to Exceed?
So it's an Exceed URL that I showed here, but the data itself are fully public. You don't need any authentication or authorization to access that data. So let me just try and bring you back to that example. So this has an Exceed-based URL, right? But that's public, right? This is a public endpoint, so anyone can access today. How can you? So right now we're partnering with them to support all the storage here, right? So no one has to like pay anything right now to like, or rather our NSF grant and our collaborations are supporting that. Where we want to go is make this a federizable, what's the word I'm looking for? Federatable model that allows anyone to contribute storage to this federation. But right now, everything is public and you don't have to pay anything to contribute data.
What about egress?
This is outside of the commercial cloud, so there's no egress charge.
Sweet.
Hi, my name is Zhong Liu from NASA Disk. It's a great talk, but the GPCB version is very dated. Right now, the new version is 3.2, available at NASA Disk.
Okay, well, so you're welcome to make a PR to this recipe to update it to point at the latest data. That's what we're going for here. So.
Okay, so thank you everyone, all of our speakers. Let's have another round of applause for our speakers. So I want to let you guys get to your coffee break, but I do of course want to plug the session that's starting at 11 a.m. I really liked what was happening in the room, talking about let's get some license on some NOAA data and some updated versions. So I want to keep seeing this sort of collaboration keep going across these organizations and initiatives. So please join us at 11. We will be talking more about best practices for cloud native geospatial. So thanks guys. See you then. Also, everyone online is welcome to join us then as well. Thanks, Ryan. It's really great. Okay, welcome back, everyone. I'm going to give everybody 5 minutes to open up this Google Doc and start to brainstorm any discussions that you were just having, or if you could reflect on the presentations that you heard this morning, the presentations you heard this morning. Did you have questions you didn't get to ask, or want to dig deeper into any of the demos? So a lot of people talked about their work, such as performance testing ZAR, performance testing GeoParquet. If you wanted to learn more about those topics, or if you wanted to ask questions, I think any of those would be good ideas for session topics. So I'm just going to give everybody 5 minutes to get settled and add their ideas to that document. Let me know if you have any questions. Okie dokie. Okay, cool. So let's get started with what we're going to do now is we're going to have everybody pitch their topics. So I can get started. I put in there the first 2 items are, I started along with some of my colleagues, some best practices guides for creating COG and creating ZAR. So with the understanding that no one solution fits all in terms of creating overviews for COG or creating chunking for ZAR, these are guides basically that we initiated to start creating some guidance for people who are trying to create these cloud optimized data stores for the first time. So I'm looking for feedback on those 2 documents or any additional questions, contributions. And then eventually I'd like to update our cloud computing cluster knowledge base with all the content that we generate today, basically. So that's my 30-second pitch. So I'll pass it off to whoever wants to volunteer to go next.
Yeah, I put one on here, just learning how to use the ESIP Jupyter Hub that we have on Amazon. So you could, close to Amazon data, of course, but you could get signed up, learn how to use it, maybe execute your first cloud native workflow.
I'll just do a pitch for mine. I mentioned PinGeoForge. We could, if people want to make some recipe contributions or even just propose some ideas, we can sort of walk through in a little bit more detail how it works and help people spin up to get to where they can contribute recipes. I also noted that this seems, the goals here are pretty aligned with the curating mirror data stores concept. So maybe I don't know, maybe we can either merge or sit nearby or find some way to interact between those two sessions.
I think that means Mirror gets to go next, right?
So I propose the one on mirror data stores. So the idea is to, I guess, see any collaboration. So we'll sit next to each other for sure. And basically, I'm looking for freebie solutions and consulting. So.
Awesome.
And I guess my name is Jim Call, and I bravely and stupidly put in cloud optimized point cloud user group. So I'm new to the field, and I'd like to learn tips and tricks and maybe establish a little community or sub-community in the Slack channel. Yep.
Hi, I'm James Gallagher, OpenDAP. So I put in this notion of let's take a look at the stack specification and how to add and write stack catalogs describing existing online data sets, particularly sort of how maybe stack can enable some of the information in an actual data set to be migrated into the catalog. I'm kind of a neophyte to stack, so we'd be learning about stack while we're doing this.
Yeah, so another thing that comes to mind is in line with this best practices guides for creating cloud optimized data stores. This could be part of that grouping of guides for creating stack and the tools, is what I'm hearing. Yeah. I think, Matt, did you propose? Oh, that was. I mean, I put a bunch of other ideas in there. So a couple other ideas that I would be interested in are going through the Kerchunk tutorial, because I haven't actually gone through it myself. Another idea, which I think was in line with the Mirror Data Stores presentation, is I think that this is a really great group to start a best practices guidance document for maintaining cloud optimized data stores. So one thing that came up when I was talking to, I don't know if Dave, did we lose Dave? No, there's Dave. So when I was talking to Dave last evening, it came up this problem, obviously we're creating a lot of duplicates of cloud optimized data across not just NASA, but also like across the industry. And people don't actually know what and this came up actually with Patrick Quinn too, who I saw was in here. How do we basically know about what other people are doing? And also the problem that's coming up is that the scientists that are producing these analysis-ready cloud optimized data stores are not necessarily versed or paid to maintain them and keep them up to date, right? So how can we sort of outline this problem and start to come at a solution through a best practices guide for maintaining these cloud optimized data stores, or saying that they're going to be ephemeral and they're going to go away and they're going to have a self-destruct button after like 6 months or something. So that was another topic that I put in there. So unless there's anybody else that wants to pitch a topic, I'm going to give everybody 2 minutes to vote on what topics. I would say limit yourself to voting on 2 so we can form some little clusters here. So 2 minutes to vote. Oh, there is an additional column that you should put your name in. Yeah, sorry. Good question. I'm sorry, what was that question? I think it's the second to last column. Yeah, we probably could have titled that better. The second to last column is where you should put your name of participant, you being the participant. Okay. Apologies. So this is going to be a little bit interesting because I think obviously there's multiple leads on, or there's the same lead on multiple topics. So here's what I'm going to propose. So I think that there is obviously a big group that's clustered around working on a recipe for PanGeoForge. So I'm going to propose, and those folks wanted to be next to the curating a mirror data store. So I think I see Maha over there and Ryan over here. So maybe Ryan could move to the 2 rows. You guys could all sort of cluster over there. You could move to the 2 rows in the back there, and anybody else who's interested in the PanGeo4 recipe and the curating mirror data stores will be over near Maha. In terms of, there's 2 groups that are interested in Kerchunk and the czar best practices, which Rich and I are both interested in helping lead. So I think we should cluster here in the middle. So the Kerchunk tutorial people and the best practices for generating czar stores will be in the middle. And then I think, oh yeah, and then the populate stack catalog. If people want to do the populate stack catalog, maybe sit over here with Matt. Did I miss anybody that doesn't have a group that they want to go to? Did anybody not hear about a group that they would want to join? Okay, cool. So now we have until 12:15. At 12:15, we'll reconvene to talk about what we worked on. Any questions? All right, let's go. You can vote with your feet too. You can do something different. This is just an initial pass.
Specifically for you folks on Zoom, once we're settled out and put computers in the different groups, we'll open up breakout rooms, and then you can manually pick which room you want to go to. So just give us a minute to reshuffle here.
All right, I'm gonna try and get you guys to lunch on time. How does that sound? Okay, so let's see. Do we have somebody from Maha's group that can report on what you guys talked about? We do 2 minutes per group.
So I guess for us, it was sort of like a therapy session. You know, we poured over a lot of the things that don't work. But it was a nice, lively discussion. So it was nice to see that, you know, we had representatives from NASA and NOAA, the data centers. So basically what we decided was, you know, we'll take one or more data sets that that we have, as well as that are out in the public already, and take it through some of the steps that are required to, you know, sort of address the issues that we identified. So obviously, if any one of you that are interested in it, that were not part of the discussion group, you know, come and talk to us. You know, we would love to continue this discussion, either as part of the cluster or just as practitioners. So, thank you.
Awesome, thank you so much. Does somebody from the Pangeo Forge group want to report out?
Sure, yeah, I mean, we didn't like put all the world's data online in like 45 minutes. But I think a core group, we made some progress. So I think a few people now understand how to contribute, what the process looks like. In trying to explain it, I realized how confusing certain aspects are, so it was useful for me, even if it wasn't useful for them. But I think what we mostly did is created new issues in the PanGeoForge staged recipes repository, documenting data sets we would like to see. And so some like synergies that happened through that project is, you know, Brian mentioned like they wanted to bring in the North America Cordex data set into through Pangeo Forge, they saw that someone was working on Eurocortex, right? So like that's a sort of collaborative interaction we want to cultivate, because then they can probably reuse a lot of the same code or same patterns for those two data sets. So I would say like that was successful, but clearly like it's more of like a 2 to 3 hour process. I think if someone actually really wants to go from zero to making a contribution. And so how can we lower that time? That's a good question.
All right, cool. Yeah, this is perhaps unsurprisingly my first time trying this format, so I appreciate you guys being good at things with me. I would say during the winter session, we did what we called a fishbowl, which is more like a discussion group all together afterwards, which was also very successful. But I think there's a way that we could adapt this format to maybe be a longer format so that people can do the tutorials all the way through, which would be great. I can start the report out for the Kerchunk tutorial. So Rich was really great in setting up how many new people on the ESIP? 5 new contributors on the ESIP Q Hub. So ESIP has its own, quote unquote Pangeo stack, not a Pangeo type stack with Dask and Dask Hub and Jupyter. So we have 5 new users of that Jupyter Q Hub from the esipfed.org Jupyter Q Hub instance. I'm going to share my screen real quick to show what the actual, you might need to actually make me a host. So we noticed a couple of issues. So the instructions for doing the Q Hub, the instructions for doing the Kerchunk tutorial include instructions for actually using ESIP's Q Hub. So we identified a couple of issues with those instructions. And so I was able to open a PR for those changes. And then we got through 1.5 parts of the tutorial. So of course, everybody likes a nice visual. So that's our visual that we got to. We got a little globe there. You're not seeing it. Oh, it's in the, yeah.
Zoom is seeing it.
Zoom is seeing it. Our 6 participants are seeing it. Yeah. We made a plot. Woo! Okay. Yeah, small wins. Okay, so then any other highlights, Rich, or things you want to share? No, we learned about Kerchunk. Okay, cool. Let's go to the last group.
Okay. Okay. So we learned about stack catalogs. So we talked about stuff. That was Doug's suggestion for the summary. But we learned about stack catalogs. So stack catalogs have 4 different components: the catalog itself, and then the collection, which is held by a catalog, and then yes. Okay. And so then items, and then assets. And so if we want to think about, say, grouping a bunch of HDF5 files in there, it turns out that the HDF5 files wind up being items, and the individual variables, for example, in those could be assets, which is kind of a neat thing. So Stack provides a way to decompose something that's much larger, and it also possibly provides a way to sort of hide some of the noise in there. So that's pretty cool. And then we talked ad nauseum about the differences between discovery and use, and where one makes a transition from one phase to another, and the fact that stack catalogs can be thought of as a kind of a data set. Have I left anything out? And also, we ruined Matt's session by dragging him into this.
Okay, awesome. Well, thanks so much, you guys, for joining. And yeah, get to my last slide here. It's not working. Slide. All right, yes, join the cloud computing cluster if you aren't already a part of it, and thanks. Lunchtime, all right.